everyone, and thank you for watching this presentation. My name is Martínez-Garzón from GFC Potsdam, and in this talk I will show you results from our analysis on different seismic sequences of moderate magnitude events in the Marmara region, as well as interaction between seismic and seismic deformation, mostly based on the data coming from the ICDP-GONAF seismic borehole observatory. And I would like to start by acknowledging the co-authors and collaborators from these studies, which you can see the main ones listed on this first slide. Seismic and seismic deformation connect very well together because in some cases slow slip transients are observed to precede seismic ruptures. This is particularly well documented in rock deformation stick slip experiments, where under certain boundary conditions and fault properties, seismic and slow precursory processes are observed before macroscopic failure. There is also the fundamental question of whether small earthquakes behave in the same way than the big ones. And in that context, there are several observations from slow precursory processes preceding the occurrence of large megathrust earthquakes, for example, the Great Tohoku Hoki earthquake in Japan, or several megathrust earthquakes from Chile. So currently, slow slip is now widely recognized as an important ingredient to understand earthquake nucleation processes. We focus our research in the Marmara section of the North Anatolian Fault in northwestern Turkey. This section constitutes a seismic gap, and a major earthquake is already overdue in the vicinity of the megalopolis of Istanbul. There, the GFZ is building PBO Turkey, with the backbone instrumentation being the 7 ICDP-GONAF seismic borehole arrays, which are here the red circles, and 6 borehole strain meters deployed by UNAFCO from the US. This downhole instrumentation is complemented with different surface networks, such as the PIRES network in the Princess Islands, the GANOS network on the western side of the Marmara Sea, and the SmartNet network in the Armutlu Peninsula. To have a general idea on how prominent earthquake interactions are in the Marmara region, we utilize the best available seismicity catalog in the region, covering about 10 years, and apply the nearest neighbor approach developed by Saliapin and Benzayon to identify foreshocks, main shocks, and aftershock sequences. Here on the right, you see the distribution of rescaled inter-event times and distances, which displays a very large proportion of background seismicity. Still, some large clusters can be distinguished, and we classified these large clusters into seismic swarms, which are basically chains of events with similar magnitude, or bursts, which are more typical main shock aftershock sequences. Earthquake swarms typically reflect a seismic transient forcing, either fluids or slow slip or a combination of both. And the main shock of the seismic swarms are here plotted on the map with the red circles, and you see that they mostly concentrate in the Armutlu Peninsula, which is a hydrothermal system with a lot of fluids present in the crust. Accordingly, the results revealed that the foreshock density is highly heterogeneous in the Sea of Marmara region, and the foreshock density is the largest around the Armutlu Peninsula. In this region, and also in the western height, which is the segment of the fault that is creeping, the probability of a main shock to be preceded by foreshocks reaches 10 to 12%, clearly deviating from the average 5% observed in standard catalogs. This map additionally reveals one more interesting thing, which is that the 5.8 earthquake that occurred in 2019 in the Marmara Sea occurred right at the boundary of two fault regions that display clearly different earthquake dynamics. Some previous studies reported the occurrence of earthquake foreshocks before the 1999 magnitude 7.4 Izmit earthquake and related them to the different earthquake nucleation models. In the following slides, I'm going to focus on the analysis of 3 different sequences, whose main shock are here plotted with the purple stars, The main processing applied to each sequence basically consists on enhancing the seismicity catalog either manually or by template matching, then investigating the seismicity patterns, whether there is localization or migration visible, and then analyzing the strain meter recordings before and after the main shock to search for slow deformation. So let's start with the first of these sequences. In June 2016, a magnitude 4.2 earthquake, which is here the yellow star, with strike-slip focal mechanism, occurred approximately 10 kilometers away from our GONAF station Teşvikiye. During the 3 days before and after the occurrence of the magnitude 4.2 event, we detected at least 61 events, in contrast with the only 9 ones detected by the regional catalog. Furthermore, we detected 18 clear foreshocks, the majority of them displaying very clear S-P and S waves and very similar S-P times than the main shock, indicating that they likely come from a similar location. In the next step, we ordered these events by time, selected moving windows with varying number of events. These are the different curves that you see here in different colors. And then we calculated the cross-correlation coefficient of each pair of waveforms and calculate the average. We see how the cross-correlation coefficients are larger right before the main shock, indicating the localization of the events and suggesting that they originate from the same fault patch activated by the main shock. Furthermore, if we plot now the graphic in real time instead of the event number, we see that the event cross-correlation stayed high up to 16 hours before the main shock. Strain meters are very sensitive instruments that are capable of detecting stress changes in the crust. From them we can get information on the horizontal strain tensor and 3 components, which are here illustrated. The aerial component represents uniform compression or dilatation of the borehole, and the red and blue curves represent the shear deformation from compression on one side and extension in the other, so that the total borehole area remains unchanged. Looking at the temporal evolution of 3 years of strain meter recordings after the typical corrections, we observe this clear strain signal in the shear components, which lasted for about a month, and it is not seen in the aerial component, which is more sensitive to vertical strain changes, for example related to barometric pressure. We found no signatures of anthropogenic noise perturbation near the Eshenkoi station during this time period, and therefore we suggested that this strain signal that we observed corresponded to tectonic slow slip. The main part of the transient was observed to start approximately at the time of the occurrence of the magnitude 4.2 event that I talked before, and also when we plot the number of seismic events and cumulative seismic moment release in the region, which is here plotted in blue, the vertical bars and the line, and we compare it with the same quantities outside the region, which are here shown in green, we see that the majority of the seismic moment released in the region for these 3 years occurred during the observed potential slow slip event. Let's move now to the second sequence. This was a sequence with a main shock of magnitude 4.6 with normal faulting focal mechanism. However, the sequence did not start with the magnitude 4.6 event. In fact, a magnitude 4.3 occurred at less than 5 kilometers about 20 days before, and then another magnitude 4 event occurred in the region but about 15 kilometers away. So we ran a template matching the Tectona algorithm in the available stations and generated a catalog of detections for about 3 months. We came up with about 2,400 events detected, which is about 20 times more than the available events in the regional catalogs. During the first 20 days of November, we did not detect any event, and then about for 4 days before the magnitude 4.3, we see some events, and then the seismicity rates after the 4.6 event substantially increase afterwards. What called our attention is that the first large event in the sequence, the magnitude 4.3, occurred after a strong change in the sea level of 0.7 meters, where a storm occurred at the minimum of the fortnightly tides, and this is the largest sea level change observed at least in that year. Then the other two largest events in the sequence also occurred during time periods of stress and loading from sea level decrease. However, again, after this magnitude 4.6 event, we identified a slow sleep transient lasting for about 30 days. This time, the slow sleep event could be identified in at least two nearby stream meters, and after doing some Coulomb forward modeling to test different scenarios for the fault source, we found that the most likely location of the slow sleep could be the shallower portion of the same fault that was activated during the rupture of the 4.6 event. About a month after the occurrence of this magnitude 4.6 event, when that slow sleep transient was finishing, we deployed a dense surface seismic network in the northern portion of the Armutlu Peninsula with the goal to connect the different GONAF boreholes and better understand the deformation processes of this interesting region. The bulk of our recorded seismicity is located in a region of about 7 by 7 kilometers surrounding the magnitude 4.6 event, and this corresponds to the seismicity from this small video containing about 1,200 absolute locations and about 850 events relocated, which together define a roughly planar structure where the main shock ruptured at the bottom and the slow slip could have activated the upper part. The main shock focal mechanism was normal faulting and displayed very good agreement with the observed planar structure. Interestingly, this seismicity following the magnitude 4.6 event occurred in 4 clear sequences containing each more than 50 events per day, and it appears to be driven by a seismic transient forcing, likely combining fluids and a seismic slip. So we change now to our last sequence, the one of largest magnitude. On September 26, a magnitude 5.8 earthquake in 2019 ruptured in the central segment of the Sea of Marmara at the transition between the creeping and locked portions of the fault. It was preceded by a magnitude 4.7 foreshock 2 days before, and in this study, again, we generated an enhanced seismicity catalog using template matching and then relocating the new detections to illuminate how this earthquake nucleated. For this sequence, a two-scale earthquake preparation process was recovered. First, preceding and following the magnitude 4.7 foreshock, these are the two upper plots here, we observe seismic activity activating all the segments that will be activated within the 5.8 rupture, and then this is followed in the plot C by a short-term localization of the seismicity around the future 5.8 main shock, lasting about a couple of hours. So this is my last slide. In summary, we first looked at the distribution of earthquake foreshocks in the Marmara region and saw that it is highly heterogeneous, where the largest foreshock proportions are found in the hydrothermal area of Armutlu and in the creeping fault section near the western high. We looked in detail into 3 specific sequences containing moderate magnitude events in the region, and we observed clear seismicity preceding the main shocks. At least 2 of these sequences present some degree of localization around the final rupture, but no clear tectonic slow transients are recorded in the stream meter data preceding these sequences. This could be because there is none, or because another signal is obscuring these changes. In that respect, we found that at least 2 sequences started after stress and loading related to sea level changes. Finally, we did identify 2 slow sleep events lasting for more than 30 days around the Armutlu Peninsula. They are observed to be preceded by the largest main shock of these sequences, and it is not 100% clear what is first, the earthquake or the slow sleep, but what is clear is that these slow sleep events do not represent only aftersleep, as they significantly exceed the duration and amplitude expected for the aftersleep of a magnitude 4+ earthquake. And with this, I would like to thank you for your attention. And I would like to leave my email here, and I will be happy to reply to your questions during the question and answer session. Thanks a lot.